Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion on georeferencing by taking this idea of control points, tie points, and using those to figure out what we actually have to do to get this CAD sketch to line up with this ortho image. Right, and so to recap where we left off, our georeferencing steps so far have been to find common points, right? And that's what we did. We determined that this point was this point was roughly this point, and this point was this point. And if you were doing this for real, you'd be a lot more accurate about determining the locations of those control points, both in the unreferenced data and the referenced data. But for the sake of example, you get the point. So the next thing that we have to do is we have to figure out what's called a transformation. So I'm going to give us a little bit of space here. So step 2 in this process is going to be to parameterize a transformation. Right, parameterize a transformation. Now, we're not going to go into the mathematics behind this because it's a lot more complicated than is relevant for this discussion. But basically what I'm talking about is this idea that we can use these control points, right? The location in the unreferenced data and the location of that exact same point in the reference data to basically parameterize, right? Or figure out what we need to do to be able to take this and make it line up with this. Now, we're not going to talk about the math, but what I want to give you guys a feel for is what kinds of things we mean when we say transformation. And what I want you to do is I want you to pause the video and I want you to think logically through what you would have to do to take this as it is right here and make it line up with this as it is over here. Right? Think through the steps of what you would have to do. Okay? Okay, so hopefully you've thought about it and you come up with a pretty good workflow here. So I want to walk through what I would do and talk about how these are examples of different types of transformations. So the first thing we would want to do is we would want to physically move it from being over here, right, on to here, right? Simply moving from one place to another, that type of transformation. So we're going to talk now about types of transformation. Right, types of transformation. The first type of transformation is going to simply be one where we move the unreferenced data around. We don't change anything else about it. We simply just move it around in space. And so right now, right, we have it over here, but we know that it needs to be over here. So to do that, we just slide it over, right? We just take this and we slide it over onto that. And that type of transformation is called a translation. Right, a translation. And a translation just moves the data, but keeps the size, shape, and orientation the same. Right, moves the data. Let's give ourselves just a little bit more space here. Right, a translation moves the data, but retains size, shape, and orientation. Right? And basically what we're going to be doing here is talking about this idea of size, shape, and orientation, and position. So we've talked about we can change translation, changes the position. Right? It literally moves it from one location in space to another location in space. That's what translation does. And that's the first thing we're going to do. Right? We're going to take this non-referenced image and we're just going to literally move it through space to put it roughly where it needs to go. That's translation. The next thing you might notice is that the actual ortho image, right, the orientation of it, right, is wrong, right? The ortho image, the sort of this protruding arc piece here, is pointing north and maybe a little bit east, but in our CAD drawing here, right, you'll notice that it's pointing north and a little bit west, right? The orientation is wrong. So once we've moved it to the right place, what we want to do next is we want to rotate it. We'd want to rotate it so that the protrusion, so that it lines up with the rotation of the actual building, right? And so that change in orientation, we call that a rotation or rotate, right? We call that a rotation, right? A rotation changes the orientation, but retains size, shape, and position, right? It doesn't change anything other than the orientation of the data, right? So rotation is orientation. Okay. So again, in this case, right, we would move it through translation and we would rotate it so that instead of pointing northwest, this arc would point northeast, right? We would match the orientation through rotation. Next, you might realize that, oh, this CAD sketch is actually larger, right? It's larger than this ortho image, right? And so the next thing we would want to do once we get it in the right place and rotated properly would be to actually shrink it down, right? Would be to shrink it down to match the size of this ortho image, right? And so to do that, right, that change in size is called scale. Right? And this is a little bit confusing because we talk about scaling in so many, or scale in so many contexts, but in this case, we're talking about scaling is changing the size. Scaling changes the size, but retains shape, position, and orientation. Right, so scaling changes size. Okay. And then if we apply these three transformations, translation, rotation, and scaling, we'll be able to take this CAD that does not have a spatial reference and make it match up to this this real world data as good as well as is possible. Right, that's what I mean when I say to parameterize a transformation, is we figure out some combination of these transformations to apply in some order to make it so that our unreferenced data matches up to our reference data. Okay. Now, there is actually one other sort of primal transformation here that I want to talk about. We wouldn't necessarily apply it in this particular instance, but sometimes you might have to do what's called skewing. Right? And what skewing does is it changes the shape by changing angles. changes the shape by changing angles while maintaining size, position, generally speaking, and orientation. And these two, position and orientation, are generally speaking. So what I want to do is I want to just quickly end this video by going through sort of a more stylistic example. So we went through sort of a realistic example here, but I want to sort of sketch out examples of how this would work, right? So in terms of translation, if we start with a square, right? So this red square is our original. I'm going to draw it in all four cases. So we have this red square in our original example. And I'm going to draw a new square in blue to reflect what the transformation does. So for translation, what translation does is it moves the data. So if this is our original, right, the new data is going to be the same size, same shape, same orientation, just in a different location. Okay, that's translation. Rotation changes the orientation, but retains the size, the shape, and the position. So what that would look like would be, imagine taking a square and rotating it 90 degrees to create a diamond, right? I didn't change the size, I didn't change the shape, I didn't change the position of the center of the data set, right? I just rotated it. That's rotation. Right? Scaling changes the size, but keeps the same shape, position, and orientation. So you could imagine taking this square and elongating all of the sides equally, right? Elongating all of the sides equally to make a larger square so it's got the same shape. Right? Skewing changes the shape by changing angles while maintaining size, position, and orientation. Right, so you could imagine right now we have, let me actually grab a different color. Right now we have, if this drawing was accurate, right, we would have 4 right angles, right? This would be a square. What we could do is we could bend the angles, right, to create something like that, right? Where we've bent the angles. These are no longer 90-degree angles. We have the same general orientation and the same general position and the same general size. We've just changed the angles. And you'll notice here that what we did not do, and I'm going to put this in big red because this is a key definition of skewing. We did not bend / warp lines, right? We simply changed the angles, right? So just to show you what I mean here, right? Right, this, so going from this angle to a much shallower angle, that's skewing. Right, going from this shape to a shape where we have a straight line on the bottom, but then we make the front line all wiggly like that, like that is not skewing. That is not skewing because we bent this line, right? Skewing doesn't make straight lines no longer straight, basically is what I'm trying to say. Skewing specifically only changes the angles between the different lines. It does not bend them. It does not make them curve. It does not warp them, so to speak. So hopefully this makes sense. When we talk about the most common form of transformation, right, and we parameterize the most common form of transformation, what we're really talking about doing is finding some combination of translation, rotation, scaling, and skewing to take the unreferenced data to make it match up to the referenced one. So hopefully this made sense. And if you have any questions, as always, please reach out. Thank you.